Hi student, welcome to this new video still on linear independence. In this video, we want to solve some practical questions. However, before getting there, let's have a little bit of reminder. A linear combination is useful in this context because it is exactly employed to determine whether a set of vector is independent or dependent. For instance, you can see that this equation here, right, is a linear combination of the vectors with the scalar. And you also realize that for the linear independency, you realize that this is actually a linear combination. But in this case, the scalar should be all zero. For linear dependency, this is also a linear combination. But in this case, the scalar, right, at least one should be non-zero. Now, let's have a look on the first example. Right, is W equals to 110 and 101 linear dependent or linear independent? Right? Okay, so let's check. Let's consider alpha and beta any scalar. So let's check therefore if they can be written as right. So we need to find alpha and beta to see if are they all zero, then it will be linear independent. Are there at least one of these two is non-zero, then it will be linearly dependent. So having said this, we have that alpha 0 plus beta 0 beta equal to 0 0, and this will lead to alpha plus beta equal to 0, alpha equal to 0, and beta equal to 0, which lead to alpha equals to beta equal to 0. So since alpha and beta equal to 0, therefore the set W is linearly independent. Isn't that simple? Now let's look at the second example. V is equals to 111 is equals to 21 minus 1 and is equal to 013, right? Is V linearly dependent or linearly independent? That's a $1 million question. So how will you attempt to answer that, right? So the first thing we notice from this set of vector is that we can write one vector as a combination of others, right? Therefore, we see that this vector can be written as a linear combination of the other two vectors. Therefore, the set V is linearly dependent, because as you can see, the scalar, this is minus 1, the scalar are non-zero. Now, from this example, right, we can give we can generalize the following. Right? From this example, yes, we can generalize the following fact that if you consider a set S of two or more vectors, right, the following statements are equivalent. Right? So we have S is linearly dependent is equal as at least one vector in S can be expressed as a linear combination of the others. Right? So these two equations are equivalent and then very, very useful, these two statements. So a set of vector is said to be linearly independent if one of the vector in the set can be written as a linear combination of the vectors that are in the same set. Now, if you want to answer the third example, right? Let's do it, guys. Let's do it. Now, show that, right? Show that V1, which is 2, 5, 3, V2, which is 1, 1, 1, and V3, which is 4, 2, minus 2, 0, show that this set is linearly independent. Okay, so we say that a set is linearly independent if we have that the sum of I of alpha I vi equals to 0 with the alpha I all equal to 0, right? So in this case, they are linearly independent if and only if alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 equals to 0 with alpha 1 equals to alpha 2 equals to alpha 3 equals to 0, right? That's the condition to be met. Okay, so we can write this in an augmented matrix form, right? Which gives me 2, 5, 3, 1, 1, 1, 4, minus 2, 0, dot, 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 right? 2, 5, 3, 1, 1, 1, 4, minus 2, 0, dot, 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 0, 0, 0, right? So the first thing is that I will do over here, right, as you see, will be to have that R2, right, will be equal to R2 minus 2R1, right? So I have that R2 will be equal to R2 minus 2R1, which leads to 2, 1, 4, and then 1 minus 1 minus 10, 3, 1, 0, dot, 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 0, 0, 0. Yes, and from here I can swap, right? I can swap R1, I can swap R1 and R2, right? So that I should have the leading entry at the top. So this will give me 1 minus 1 minus 10, 2, 1, 4, 3, 1, 0, 0, 0, 0, right? So having this this way, the next thing to do, right, will be to replace R2 by R2 minus 2R1 and to replace R3 by R3 minus 3R1. So this will lead to exactly 1 minus 1 minus 10. If you solve that carefully, right, you will have that is equals to 0, 3, 24, and 0, 4, 30, 0, 0, 0. Right, so I can divide the second row by 3. So this will give me R2 divided by 3, right? So I will be coming to 1 minus 1 minus 10, 0, 1, 8, right? And then I will have 0, 4, 30, right? Which is 0, 0, 0 over here. Now, in this equation now, I can now have because I need to have 0 below the leading entry of row 2. I need to have 0 here and eventually 0 here, if you still have time and space for that. So I'll do R3 equals to R3 minus 4R2, right? And this will give me exactly 1 minus 1 minus 10, right? 0, 1, 8. And this will give me 0, 0, minus 2, dot, 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 0, 0, 0. Right. Okay. So for the sake of time, you can see that I can still choose. I can still just divide R3 by minus 2, right? And this will give me 1 minus 1, then 0, 1, 8, 0, 0, 1, right? And 0, 0, 0. So from here we can already see that I have my leading entries here, and then I can see that and my alpha from the 3 equation, I can see that alpha 3 from here will be 0, and if alpha 3 is 0, I will have also alpha 2 here 0, and then I will have also alpha 1 be 0. So we see that obviously you can still reduce, right? But from here we see that alpha 1 equals to alpha 2 equals to alpha 3 equals to 0. So we have that. So we have that the set of vector of v1 v3, the set of vectors of v1 v2 v3 is linearly independent. Thank you very much.